Welcome everyone to our third in the series of Heroes of Herbivory webcast. So we would really like to welcome all of you participants. We've got 107 now, so that's great. Probably more will join. My name is Melanie McField, and I'm the Director of Healthy Reefs for Healthy People with the Smithsonian Institution. I've got my co-host today, Patricia Kramer, the Director of Atlantic and Gulf Rapid Reef Assessment. And we have a distinguished panel, which Patricia will introduce in a moment. I'm gonna first go over the housekeeping of how we're gonna run this webinar. So all of you participants will be listening and asking questions whenever you like during the presentations from the Q&A box down at the bottom, kind of over close to the more lower right Q&As. You can direct it to one of the presenters by putting their name at the beginning of the question and then write the question. We're gonna hold all those questions until the very end. So we're gonna go through all the talks and then get to the questions. You're not able to use the chat function, so it's just a question to us, the presenters. And the other thing I would mention is that over in the top right where you see gallery view, you can click on that and you can what do you call it? You hide the thumbnails while the talks are going. So you won't see our faces or our little names then, and you'll get a full screen view of their nice presentations. So I'll turn it over to Patricia for the introductions and let's get going.
Hi everybody, my name is Patricia. I'm very excited about being here for a very special topic on diadema restoration. I'd like to take this opportunity to thank all of our panel speakers today and also to introduce them to you. To start off the conversation, we have Harilaos Lessios. He's with the Smithsonian Tropical Research Institute based in Panama. Joining us from Puerto Rico is Stacey Williams. She's with the Institute for Socio-Ecological Research. Over in the Eastern Caribbean, we have Alwin Hylkema. He's with the University of Applied Sciences, Van Hall Larenstein. All the way across the pond is Max Bodmer. He's with the University of Lincoln, and he'll be joining us in talking about some of his work in Honduras. Ian Drysdale is with the Healthy Reefs Initiative. He lives in Roatan, Honduras. And rounding off the discussion is Joshua Patterson, and he's with the University of Florida in Florida. So welcome to the panelists. At this time, I'd like to ask Harilaos to go ahead and share his screen, and for the other speakers to please turn off your video and turn off your mic. And we're going to get started with Harilaos. Again, as Melanie said, if you have questions, please type them in the Q&A and we will answer them at the end. Okay. Welcome, Harilaos.
Okay, good morning, everyone, wherever you might be. As Melanie said, I'm Harilaos Lessios, and I'm here to talk about what happened to diadema, and why it happened, and what's happened since then. Everybody knows, actually, that what happened was that diadema died. That happened back in 1983. It went from being very abundant to being very rare. That was 37 years ago. That's in geological time, that's not very long. In human lifetimes, it's quite a bit. Some of you weren't even born back then. So this is basically a paleontological talk delivered by a fossil. Diadema all over the Caribbean was very abundant. And in 1983, all of a sudden, we started noticing that on various reefs, it started dying with very characteristic symptoms that no other causes of mortality have ever caused. And I and my colleagues here at STRI were able to trace the progress of this mortality front through communication with various places in the Caribbean. The mortality started in Panama in January 1993. It started spreading north This is the white arrows here is the spread of the mortality. These are currents, the black arrows. It went to north and it also went east. It got all the way to Bermuda. From Florida, it actually started moving against the current from one locality to the next, from north to south. Its advance ended in January '84, a year after in Puerto Rico, a year after it started in Panama. The populations crashed. This is data from the San Blas area in Panama. This is pre-mortality densities here. Note that the scales are different. Once the mortality hit every reef, and it took about 2 weeks between the appearance of the symptoms and the disappearance of diadema, then it just stayed to pretty close to zero. All over the Caribbean, the average mortality was 98%. Only 2% of diadema survived. There's no locality in the Caribbean known to have escaped the disease. People were becoming worried because where diadema is present, the algae are being eaten. Where it's absent, they overgrow the coral. Coral is good. Algae are dead, so they inhibit recruitment of corals, and therefore the reef, when it stays at an adult stage, will eventually turn into sand. Now, why did this mortality spread? What was the agent that spread it? The answer is we don't know. We failed to identify what is suspected was a pathogen, but all the indirect evidence suggests that it was a pathogen, not the pollutant, not the heat from El Niño effects, because the mortality was just as severe at the end as it was in the beginning, not what the pollutant would do. It only affected one species of sea urchin. It generally moved in the currents, except where localities are close together. And piece of circumstantial evidence in aquaria where they were fed by seawater, but otherwise didn't have any contact with other sea urchins. They also died. Now, we continued monitoring the populations long after the mortality. The reason I'm showing this is because there's something quite relevant to restoration efforts. You will notice that in some reefs, there have been successful events of recruitment. They don't seem like much because the scale is made to accommodate the pre-mortality densities. But the important point is that 1 year the sea urchins were there, the next year they were gone. Here it lasted almost for 2 years. Presumably what settled succumbed to the natural causes of mortality, which means that obviously a lot of diadema need to be put in order to have diabetes from one year to the next. Now it was suggested that in fact the pre-mortality densities of diadema were not natural. That they were caused by the by overfishing, which removed predators and competitors. So in that sense, the mass mortality might have been some sort of natural adjustment of what was previously a non-natural phenomenon. To test for this, we actually collected mitochondrial DNA from populations all over the Caribbean, and also from Diadema mexicanum in the Eastern Pacific, and what's now known as Diadema africanum on the African coast. One thing to notice is that even though these collections are made after the mass mortality, year 2000 or so, the effects of the mortality had no genetic consequences. The Caribbean, Diadema antillarum, has a heck of a lot more genetic diversity than either Diadema mexicanum or Diadema africanum. And this is not the result of our having collected many from many populations, because it stays true if you analyze each population separately. Given that, we could actually use models to calculate when the populations of Diadema expanded. This one is the so-called mismatch distribution. I won't go into the details. The answer, given the variation that exists, was that Diadema started expanding its populations about 200,000 years ago. Confidence limits, no, not more recent than 100,000 years ago. If you analyze the same data with coalescence models, using the mutation rate that you need to actually convert divergence to years, came from the Isthmus of Panama. Because of the uncertainty about the Isthmus of Panama, we use two mutation rates. But basically, no matter which you use, it turns out that at about 200,000 years ago, there were maybe about 5 million females in the Caribbean, female Diademas in the Caribbean. So it seems that no, the Diadema expansion started long before humans started fishing in the Caribbean, and that the pristine reefs of the Caribbean, if you go back to say the 1500s, had just as many Diadema as now. Okay, so the diet, now what happened next? I have plotted here the densities of the most recent survey of Diadema in places where there were pre-mortality data. And the answer is, I mean, there are many problems with this data are not always comparable even within the same locality, but basically the signal overwhelms the noise. The Diadema has been between 5 and 15% of the most recent time it was looked at, between 5 and 15% of what it used to be back before 1983. In Jamaica, the north coast of Jamaica is where the highest recovery has happened. It's about 53% of what it used to be. Why haven't they recovered? Diadema produces about 1 million eggs per spawning. It spawns every month in new moon in the tropics the whole year round. There are a lot of eggs around, but not many adults. One possibility which would be very worrisome for any restoration type would be that in fact the pathogen is still around and wipes out whoever settles. We don't think that's the case because on 2 incidents of recurrence, we could see Diadema with the same symptoms, and they are characteristic as having occurred. So the rest of the time, the Diadema that are around seem to be unaffected by any possible pathogen. I and many other people try to assess recruitment. We set those panels that Rolf Bach had actually settled in Curacao and was getting a lot of recruitment before the mass mortality. And I also set a different kind of trap. Bach was getting about 13 juveniles per meter square per day before 1983. What people have been getting around the Caribbean since then is a lot less. The highest rate was actually by Stacey Williams, who gave the next talk, which was not on panels like the one that showed. It's slightly higher, but still a lot less than it used to be. So we think it's an alley effect. We think that the populations actually, there are too few adults to for efficient fertilization to produce enough larvae to overcome the natural sources of mortality. I'm sorry, I haven't kept the time. How much longer do I have?
It's pretty much up, Harris.
Okay, so I will skip this part and come to the conclusions. What happened was 98% of Diadema died. Most likely the cause of mortality was a disease. I don't know what kind of pathogen. It was not an adjustment of previously unnatural high densities. And the average recovery since then, perhaps not to the present day, but at least a few years ago when people last reported results, is 12%. And we think that the lack of recovery is because of the lack of sufficient larval supply. Thank you. The next speaker will be Stacey Williams from the Institute of Socio-Ecological Research, Coastal Survey Solutions, and she will speak about a success story.
Thank you, Harris. Can everyone see my screen? Okay. So good afternoon. Today I am going to briefly talk about what I've been doing here in Puerto Rico for the past couple years regarding diadema restoration here in Puerto Rico. So the diadema restoration project started in like 2015. And what we do is we collect post-larval settlers, and we bring those settlers back to lab, and we grow them in the lab until they're young adults, between 3 to 4 centimeters in test diameter. Once they're young adults, we then move them to the different reefs to boost their populations around Puerto Rico. The overall goal of this project is to enhance reef condition by decreasing, decreasing algal abundance and increasing the survivorship of coral adults and settlers and other benthic organisms. So what we're seeing right now in Puerto Rico is a spread in this encrusting algae called Ramicrusta. And Ramicrusta is a pacynalid, and you can see in the picture to the left, it's golden reddish color. And on the east coast of Puerto Rico, the abundance of Ramicrusta is really high. You can see up to 60 to 70% on some of these reefs. And what's dangerous about this algae is that it can overgrow corals, like you see in the top right-hand corner of Obracella annularis. You can see that Ramicrusta is kind of encroaching on the live tissue. On the bottom right-hand picture, you can see that I scraped off a little bit of the Ramicrusta, and you can see the dead skeleton of the Obracella. So this is what we're seeing is in the field is we don't see any parrotfish scrape marks on this algae, but what we have noticed is that when we see diadema and other sea urchins like Echinometra, there's a decrease in Ramicrusta abundance and even an absence. So another goal of this project now is can diadema reduce Ramicrusta abundance around Puerto Rico? So how I collect post-larval settlers, and I was lucky way back when doing my dissertation research in 2010 to find a hotspot of settlement. So we've been placing between 30 to 40 mooring lines at the shelf edge in La Peguera. This year we have 40 mooring lines. On each of these mooring lines, we have 20 settlement plates. And these settlement plates are made of artificial grass called astroturf. You could find this in Kmart sometimes, Amazon. And these plates are dangling in the middle of the water column between like 35 feet. So these plates are collected and replaced every month from May to November. Since COVID is currently happening, we had to postpone deployment of the lines. So we'll be collecting the first set of plates next week, hopefully, and we'll be continually collecting them until December. So these plates are brought back to lab, and we gently remove the settlers, and you can see the settlers are beautiful. Not saying that the adults are not beautiful, but they're usually red in color, and they range in size. Settlers that we usually collect range in size between 0.4 millimeters to 1 millimeter in test diameter, and you can see in the right-hand picture, they do range in sizes when they settle. They could maybe settle earlier in the month before we collected. You could see a small little settler on the top right hand, and then a larger black settler in the middle of the screen. So these urchins are then placed into a couple different systems. When they're really small, they're very sensitive. So you need to have the tanks well maintained and keep the quality of the water constant, because they'll start losing their spines. But once they become hardier, and then we move them to the outdoor wet tables, and we feed them like twice a week a range of different algae. And these urchins are in the water tables for about a year until they reach about a young adult stage between 2 to 4 centimeters in test diameter. So when they're ready to be restocked, we then move them to the reefs. And this is a map of the different areas where we have restocked Diadema. So far we've restocked about over a couple thousand. And this summer we will be restocking on the West Coast in Cabo Rojo, Fonduco, and Guanaquilla, and also in La Parguera. I have about 750 sea urchins. But today I'm going to be talking about some of the results from an East Coast reef, Fajardo, called Cayo Diablo, and also last year's restocking event, one of the reefs, El Corral, which is located in La Parguera. So before we do any restocking, we set up these enclosures called corrals. They're the experimental units, and we have 6 enclosures per site. These are just made of metal chicken wire, and the area of these corrals are about 4.5 square meters. We'll be using probably smaller corrals this summer. To measure the change in benthic substrate, we use quadrats, and we have 3 random quadrats and 3 fixed quadrats per corral. We do have a control at each site, and we've been placing between 23 to 25 diadema per corral, and then the rest of the diadema we usually release on the reef. So the benthic cover and also diadema tension is monitored, and this ranges depending on the site. Usually 1 week after restocking, 2 weeks, 1 month, and then 2 months. So here's some results from Cayo Diablo, Fajardo. This was in 2018. As I mentioned, East Coast, there's a lot of Ramicrusta, and this is just, this is the mean cover of the fixed quadrats in all corrals. And you can see that Ramicrusta is really high. It's close to 60%. You don't have what I'm calling pavement, it's clean substrate. And you have some dictyota. So let's see what diadema after 1 week. Well, Ramicrusta is a little bit decreased. You can see pavement, clean substrate has been increased. Again, Ramicrusta has been decreased, pavement and filamentous turf algae also increased. And then after 2 months, you can see that Ramicrusta has been significantly reduced, 54%. As I mentioned, this is a mean of all the corrals in just the fixed quadrats, but in some of these corrals, Ramicrusta was reduced up to 80% within 2 months. So they are effective grazers. And you can see that pavement clean substrate is also increased. Just to give you an example of what they can do in 2 months, this is before any restocking. You can see that the ramicrusta is a golden brown color with dictyota, and you have some pasonalids. And then after 2 months, you can see that the substrate is really well grazed. It's very clean compared to what it was 2 months ago. So we're going to move to the southwest coast of Puerto Rico in La Parguera in 2019. This is a different habitat. These reefs are usually dominated by fleshy macroalgae, and then we get a lot of this thick turf with sediment, which could impede corals from settling or coral survivorship. So again, this is the mean cover of the fixed quadrats and all the corrals. So this is pre-stocking. You can see there's a high abundance of dictyota and also turf with sediment. You barely get any clean substrate. So after 1 week, you can see right away dictyota is significantly reduced, and also turf with sediment is reduced. Pavement is also increased in cover. Again, after the 2 weeks, reduced dictyota and turf with sediment, even more so after 1 month. And after 2 months, you can see that turf with sediment is barely there. Dictyota, again, barely there. And we see a lot of clean substrate in the pavement. So, and within 2 months, Diadema reduced the algae dictyota by 92% and turf with sediment by 84%. So this site, I don't have the best picture because this site is very turbid. There's a lot of marine snow, but it kind of gives you an idea of what the substrate looks like with a lot of dictyota. It kind of looks dirty with a lot of turf and sediment. But after 2 months, Diadema kind of brightened the reef, and you can see that the substrate's really clean. There's CCA that is visible that maybe was hidden under the turf with sediment. So in conclusion, post-larval collection and culture can be an alternative technique if you want to do Diadema restoration and you don't have the equipment or to larval rear Diadema in lab. We'll hear later on, but it's a difficult process. As we've been seeing is that Diadema are effective in reducing fleshy algae and also turf with sediment and ramicrusta, which is very hopeful since ramicrusta is spreading all around Puerto Rico and in a lot of places in the Caribbean. The grazing impacts on algal cover were evident after 1 month of restocking Diadema. And we believe that densities, if you're going to do any restocking, should be greater than 1 individual per square meter. A master's student, Manuel Omeda, he just finished his thesis work, and he looked at what was the ideal density to restock, ideal density of Diadema to restock to the coral reefs of Puerto Rico. And he found that it all depends on habitat, but that it should be at least 5 individuals per square meter that you should restock. So the results of this study highlights the importance of herbivores in improving conditions on coral reefs. And here's my email if you want to email me for anything, and I can answer any questions. And I will then hand it over to Alwin. Thank you.
Thank you, Stacey, and good morning all. I'm going to tell you something about the Diadema booster that we're trying to develop, which is a way to restore Diadema populations on the reef, so without getting the Diadema out of the water. And I prepared this presentation together with my colleague, Tom Weyers, and I'm going to tell you something about the booster, but also about the first results of the experiments we conducted. So This is Tom and myself. Tom is to the left looking at the diadema, and I'm on the right looking at the camera. We're working for the University of Applied Science van Larenstein in the Netherlands. And the question might pop up to you, why is a Dutch university interested in restoring diadema populations in the Caribbean? Well, there's quite a few Caribbean islands that have a strong connection with the Netherlands. They're the islands of the former Netherlands Antilles. So Aruba, Curaçao, and Bonaire in the south, and Sint Maarten, Saba, and St. Eustatius in the Eastern Caribbean. And this project is conducted on St. Eustatius and Saba, and also in our marine lab in Leeuwarden, which is in the north of the Netherlands. So the status of the diadema populations of on Saba and St. Eustatius is more or less the same as on most of the Caribbean coral reefs. It's ecologically absent from all of the natural reefs, or almost all of the natural reefs, but there's locally high population densities at breakwaters and harbors, as you can see on the picture. So mostly very shallow, sometimes a little bit deeper. So we were interested in, together with the local nature management organization, Saba Conservation Foundation, Estinapa, we were interested in restoring the diadema populations. And we're looking at the different options. And of course, there's been a lot of effort in cultivating and reproduction of diadema in captivity, in transplanting diadema. Stacey just explained the method of collecting settlers, kickstarting them, and reintroducing them. But in the RAAC Pro Diadema project, we're working on enhanced settlement and survival on the reef, because we have some indications to think that certain reefs have a high suitability to do so. And that's because we placed some pilot panels. Harilaos Lessios showed us an example before. And we placed those panels on reefs on stage, no adult population whatsoever. So we were quite surprised to find a relative high number of young diadema there. So that's very interesting. And it showed us that this is the life cycle of diadema. Here we go. And it showed us that the larvae are apparently there, but the adults are not. So they either do not settle on the natural reef. It could be that they only settle on our plates, but not on the natural reef, or they do not survive there. So the focus of our project is here on the settlement and survival. We want to find out if it's either settlement or survival that inhibits recovery, and also what can we do, what kind of interventions can we use to make it possible again that they settle and that they do survive. So that's basically, these are the aims of our project. So we want to find the cue and the ideal structure to enhance settlement of the diadema larvae. We want to look into the ideal shelter and artificial habitat to maximize survival. And third, we want to identify reefs with a high settlement rate and low predation rates, because we think those reefs are most suitable for natural recovery or assisted natural recovery. The overall project aim is to combine the queue and the shelter into a diadema booster that can restore diadema populations on the reefs that we identify based on the high settlement rate and the low predation pressure. And this is a 4-year project, and we just started with it. So we have no idea how the diadema booster is going to look like, but this is an artist impression, how it could look like. Probably it will look quite different than this, but at least if it works, it will start to look like this. So some first results of the experiments we're doing. And like I explained, part of the experiments are conducted in the Caribbean and part are conducted in our marine lab in Leeuwarden. And these are the broodstock tanks. So adult diadema are kept in here. This is my colleague Tom using the shaking table to take care, to keep the larvae of the diadema in suspension. And this is one of the flasks with larvae of around 20 days. So they're doing really well in the bottles, and we try to produce them, the larvae, until competency, so we can check what cues are responsible for making them go through metamorphosis and to settle on a substrate. And we had a little bit success with that already. In the next picture, you can see small, tiny juvenile sea urchins that settled on the flask. So I think we're ready to start with the settlement assays now, and to try different cues to see to which the Diadema larvae react most, and which cues can induce them to go through metamorphosis. This is a nice way to produce a small number of juvenile sea urchins or larvae, but might not be the best way to produce large amounts. But for us, it works. So then some results from Seba and St. Eustatius. So we used the method explained by Stacey to look at recruitment on different locations. So on 8 to 9 different locations, we placed a rope with a buoy, and on every rope we placed 5 artificial turf collectors of 10 times 10 centimeters back to back. And we did this on both Seba and Stacia, but I will tell you a little bit more about the results from Seba now. So on Seba, we used 9 different locations all around the island, as you can see on the picture here. And these are the results. The graph shows the average number of Diadema per location, per square meter, per year. And what's really striking is that the differences between locations are so big. Some locations have more than 1,000 Diadema per square meter per year, while others have almost none. And it's important to know that most of that recruitment is actually happening in a couple of months, mainly May till September, and the other months have really low settlement rates. So these locations are ordered clockwise around the island, and so the green location is the first one on the graph. So that's the Fort Bay location, and then we have 3 locations with yellow crosses marked on the map, which have a relatively high recruitment rate, and they are all to the west of the island. And then we have some locations more to the east of the island with almost no recruitment, and we have some locations with intermediate recruitment. And what's really interesting is that the green cross on the map harbors the only significant adult population of Diadema on the island. So and all the locations with high settlement rates are downstream from this area. So well, we know that Diadema larvae have to be in the water for at least 30 days. So it seems maybe far-fetched that the settlers on the yellow locations are coming from the green location, but maybe it could be because yeah, currents are going around Seba, or eddies are going in the on the west of the island. So maybe that could be an explanation for the high settlement rates we find there. Some conclusions of this talk. So some reefs on Seba and also on St. Eustatius have potential for assisted natural recovery with help of the Diadema booster that we're trying to develop, because we see really high settlement rates here. Some reefs have almost no natural recruitment at all, so they need other restoration methods, like kickstarting in aquaria or like cultivating Diadema. The most important questions that we're focusing on coming years is in Leeuwarden, which cues induce settlement, and on the islands, are Seba's and also Stacia settlers from locations that receive high recruitment, are they produced locally? So we're not doing this research all by ourselves. It's quite a big project, and we have a lot of partners. Wageningen University, Wortel, the Nature Management Organization, St. Eustatius, National Parks and Sable Conservation Foundation, Dive Shop Golden Rock, the Caribbean Netherlands Science Institute, University of Applied Science, HZ, Isaac Reef, and Stacey Williams helped us a lot with designing the experiment, the recruitment experiment. And then University of Florida helped us a lot with establishing or spawning protocol and establishing a larviculture. So thank you very much for all your help, and I hope we continue the collaboration in the coming years. Here's my my contact details. So if you want to get in touch for any questions, please feel free to email me. And thank you very much for organizing this webinar. And I'm now giving the floor to Max Bodmer.
It would also help if I unmuted myself as well, wouldn't it? Hello, everyone. Good afternoon, as it is over in the UK right now. So I'm really excited today to be able to talk to you about some of the research that I've been doing over in Honduras for the last 10 years or so, as part of my PhD research and then through to my postdoctoral work beyond that as well. So my focus has been actually based on a very unique, oh sorry, we were asked to put in a photo. So this is a photo of me on the beach at my research site. I spend most of my summers for the last 10 years out on Honduras, and as you can see in this photo, I have a horrible time, absolutely miserable, and worst enemy. Staring out the window here on a grey English summer's day. There's nowhere else I would rather be. So I've been quite ambitious in what I want to cover in this talk, and I've divided it into 3 separate sections. My bit is showing off because the area that I work is a very, very unique reef site within the Caribbean, and I think there are quite a few of you attending this webinar that have had the privilege of also diving on Banco Capiro, so you'll be able to attest that I'm not lying when I go into details about how amazing this reef system is, both in terms of its hard coral cover, but also in terms of its post-mortality diadema populations as well. I'm then going to go to talk a little bit about what we've done, how we've exploited the fact we have access to this very unique reef site. And basically, we've done a few ecological comparisons between this unique reef site and other more typical Caribbean reef systems to see if we can ascertain any ecological barriers that could be hampering wide-scale recovery of diadema alongside the algae effects that have been covered by the 3 speakers that have spoken so far. And then lastly, I just really want to present just some very early stage findings from an artificial reef study that was conducted over a period of 3 years that's had some slightly promising results, with the caveat that this was a very small study and there's still a lot of work to go. Okay, so for my part 1, as I said, I really just wanted to show off and tell you where I've been diving for the last 10 years. So this here is a photograph of a reef system called Banco Capiro. And this is not photoshopped. This is what the reef looks like. It's an absolutely incredible reef system off the north coast of Honduras with really very high coral cover and really quite significant post-mortality diadema populations as well. Tella Bay, so this is Banco Capiro is located within Tella Bay, which is on the north coast of Honduras. You basically get in a boat, you drive 8 kilometers north, the captain stops the boat, tells you to get off the boat, you can't see land, and you just have to trust that eventually you're going to see a reef underneath you, and lo and behold you do. You see this absolutely incredible reef system with all of that lovely coral. Along its east-west axis, it's approximately 11 kilometers long, and it has a really unusual deep offshore topography. So the reef flat sits at about 10 meters, and there's nothing shallower than that moment. There's been a lot of work in recent years to try and get some protection in place for Banco Capiro and other systems within Tella Bay, and a lot of the people who are responsible for making that happen are in this webinar today. And in 2018, they were successful in creating, and I'm going to butcher this, and I apologise, I think there's a lot of Spanish speakers in here, and I'm going to show you my uncultured British side, that the area is now protected as part of the El Refugio de Vida Silvestre Marino de Tella, or as I like to call it, the teleprotected area, because I'm a very unsophisticated person. So why is Aquapiro so special? What am I kind of showing off about here? So the main thing that really strikes you, and you see it immediately as you hit the reef, is the incredibly high hard coral cover. So I've been doing transect and research on Banco Aquapiro since 2013, and I've been assessing it every year until 2018. I was actually meant to be there at the moment, but obviously global circumstances meant that wasn't going to be possible. But at 10 meters in 2018, we recorded a hard coral cover of pushing 70%. And there are some transects that we conducted where it was 100% coral cover along those transects at 10 meters. And even down at 15 meters depth, we have this, we still have very high coral cover at 55% as well. So you have this incredibly high coral cover, relatively low macroalgae cover of about 18% at 10 meters and about 28% at 15 meters. Unfortunately, we have seen a slight increase in recent years. So there has been a bit of an increase between 2016 and 2018, which could have something to do with the fact that there's a huge amount of riverine input that goes into Teller Bay. But perhaps the key thing and the most relevant thing to our discussions today is the fact that there's this incredibly large post-mortality diadema population. At 10 meters, individual densities vary from about 1 to 2 individuals per meter squared. Again, we've seen a decrease in recent years. So if I were to put this average here, 2014 to 2017, then that number would be 2 to 2.5 individuals per meter squared. It's a real shame I wasn't able to get there this summer in order to see whether or not that blip in 2018 is real or whether or not it's just noise in the city. So having access to this very unique reef site where we have very high coral cover and very high post-mortality diadema populations has enabled us to do comparisons with other more typical Caribbean reef systems to see whether or not there could be ecological factors that are suppressing recovery throughout the wider Caribbean. So what we did in 2013 and 2014 is we did an ecological comparison between Banco Aquapiro and reefs around the island of Utila, which is located about 60 kilometers away. We've classified Utila as a typical Caribbean reef, perhaps unfairly, and I apologize if that's offensive to anyone here, but that's because at 10 meters there's hard coral cover of about 12%, macroalgal cover of about 45%, and very low diadema population densities that are similar to that which have been recorded elsewhere in the reef. We basically compared lots and lots of different ecological variables, and the variable that seemed to account for the difference in population sizes between these two sites was the fact that on Banco Aquapiro you have all this lovely coral, and that coral is providing 3D structure, which is ultimately facilitating larger urchin populations. What's also probably happening is the structures are enabling urchins to be closer together and also reducing that alley effect that was spoken about by both Harris and Stacey earlier on today as well. So this was a kind of a correlative study that was congruent with a lot of other research out there that is showing how important habitat structure is for protecting diadema and facilitating their recovery. And we wanted to kind of confirm this hypothesis by using some fancy new technologies. So we did some 3D modeling on reefs where we compared the complexity of areas where you have urchins compared to areas without urchins. We did this using structure from ocean photogrammetry, which is a fancy way of saying we got a GoPro and we filmed some areas of reef that had different, that some that had urchins in and some that didn't. And we calculated something called fractal dimension, which is essentially a measure of 3Dness of the reef that ranges from 2 to 3, 2 being flat, 3 being completely three-dimensional, so a filled-in cube. The advantage of this approach is that you can break it down by the spatial scale that you want to be looking at. So we were looking at how the structural complexity in areas that are inhabited by urchins versus areas that aren't inhabited by urchins differs at the 5 to 15 centimeters spatial scale. We chose that scale because of the kind of because of the mean test diameter of these urchins. It seems to be the most ecologically relevant spatial scale to diadema. So what we did, we went out, we conducted a study on Utila, and we basically surveyed areas that had no urchins, and we surveyed areas that had urchins living within them. And surprise, surprise, what we found is that yes, in this middle column here, you can see that there was a difference in the fractals I mentioned. So in the 3D complexity at the 5 to 15 centimeter scale, and urchins preferentially lived in the areas that had that higher level of habitat complexity. This is not a surprise to anyone. There's plenty of literature out there that is demonstrating how important habitat structure is for diadema, but this is a slightly more experimental approach rather than looking more at the correlative approaches that have been addressing that in the past. So that kind of leads me on to my conclusion, really, and kind of the final part of the work that I've been doing out in Honduras, which is now that we've kind of established how important habitat structure is for Diadema antillarum, what can we do about it? How can we turn that into an active conservation strategy or restoration strategy within the Caribbean? And what in 2015, there's a very degraded patch reef system in the southeast corner of Tela Bay called La Ensenada. And we basically deployed 30 experimental artificial reefs in this area and monitored them over 3 years in order to establish whether or not provision and enhancement structure can help to increase populations. You can see here really sophisticated. We basically put some breeze blocks down, which I think the majority of you are Americans, so I'm going to say cinder blocks. I think that's what you call them. So basically put down some cinder blocks, the reason being that they're cheap and widely available. So if this is a strategy that's going to be able to be applied within the wider Caribbean, we want those materials to be easily accessible. We monitored the reefs over a 3-year period. And as you can see here, we also looked at control reefs. On this graph here, you can see the yellow lines of the control reefs. The populations of both adults and juveniles remained stable over the study period, whereas around the artificial reefs, you can see that there were significant increases in both adult and juvenile populations. I think the really key thing to highlight here is this massive increase that occurred in the juvenile populations, a 6-fold increase from 2016 to 2017. It's really highlighting how important the addition of that complexity is to the juveniles so that they can survive into adulthood and therefore start to contribute to future generations. Now, this is a really, really positive sign, and we're now thinking about ways that we might be able to scale this up as well. That's a whistle-stop tour. Obviously, lots of people involved in this project, lots of acknowledgements. I'm going to pass over to Ian now, who I think is going to talk a little bit more about some of the things that I have talked about here. Thank you.
Thank you. Good morning. Thank you, Max. It's a pleasure to be here today. I live on the beautiful island of Roatan. This is a picture of me pre-COVID. And as you can see in the video, things have changed a little bit since we've been in lockdown. Let me talk to you about a little bit of the restoration that we've done with urchins. Here is where Roatan is located in the Mesoamerican reef ecoregion. And here's a little bit about the Reef Health Index developed within the Healthy Reefs Initiative. Basically, we look at 4 important indicators on reef, and on the upper quadrant of that circle, you'll see fleshy macroalgae. And this is a number comparing all 4 countries and all of our sites, and macroalgae cover is around 20%. And if we look at this over time, over our 6 report cards that we published over the years, and you keep your eye on that upper right-hand section of the circle, that's fleshy macroalgae. And we can see that over time, this indicator has always been poor. That means that fleshy macroalgae has always been very high. If we look at this trend over time, over the 4 indicators per country, we can see that that brown line is usually very high. In Mexico, we see a correlation of protection of herbivores and a reduction in fleshy macroalgae, but more so in Belize. Belize has been protecting their parrotfish and their herbivores for many, many years. And you can see that amazing increase in herbivorous fish biomass and that very important reduction in fleshy macroalgae cover. Whereas in Guatemala and Honduras, the story is a little bit different. Guatemala started protecting their parrotfish 5 years ago. So we will see, we are seeing and we will see a much better, much higher increase in the herbivorous populations. Whereas in Honduras, we are very sad to say that over our last 2 reporting periods, we have seen a very large decrease in our herbivorous fish. And we are assuming that this will also mean a higher increase in our fleshy macroalgae cover. There are 2 very important grazers on the reef that we understand. Definitely parrotfish play an important role, and we're grateful that they're being protected at different levels in the 4 countries. But algae overgrowth is really creating an imbalance and an unfair competition for substrate on the reef. So we really need to see how we can bring these urchins back. When we look at our data and we compare fleshy macroalgae cover on our sites compared with presence of diadema urchins, we can see that where we don't have diademas, fleshy macroalgae cover is higher. And where we do have diademas, fleshy macroalgae cover is lower. So we need to get these important grazers back on the reef. For this pilot project, we selected 2 sites on Roatan, one in Half Moon Bay on the northwest side, and one in Dixon Cove, which is about kind of about the middle part of Roatan on the south coast. And the reason why we decided on these 2 sites is that Half Moon Bay in the west area has a wastewater treatment plant where about 98% of the population is connected. So we understand that the anthropogenic input of sewage is much lower on that site than what it is in Dixon Cove, which is an area with a relatively similar amount of population where they don't have any kind of treatment. So what did we do? Went to the market, bought a couple of these buckets, and started experimenting. And the best one that worked so far was a little bit of wire chicken mesh, then grabbing 4-inch PVC pipes and also some 1/2-inch PVC pipes. And then you pour concrete into it. Concrete and PVC are very cheap here on the island. It's very easily accessible. And once it's dried and cured, it's very easy to remove the 4-inch pipe, allowing these holes you can see on the pictures, where we then place these onto the reef. Using an extra BCD plus the buoyancy that you can control in your own BCD, it was very simple to lower these domes, these urchin apartments down onto the reef, and then you just find a clean substrate where you don't have any live coral cover. With a couple of rebar, couple of sledgehammers. It's a little bit of hard work depending on what substrate you place your dome upon, but then just a little bit of hard work underwater and hammering these rebar into the reef holds the apartment or the dome in place. This was how we set up these. Here on the left side, you see the configuration we had to follow for Half Moon Bay due to the depth. And then due to the depth in Dixon Cove, we installed the domes in more of like a line pattern instead of the cross like we did in Half Moon Bay. Once these were installed, we did pre-urchin agrabenthic transects. These are 10-meter long transects, and we decided to always follow the 4 cardinal directions. So there's a transect in each of the cardinal directions heading out from the dome, and each dome is separated about 20 to 30 meters from each other. So per site, we have around 20, we have exactly 20 transects. We then collected urchins in the nearby area. It was not easy finding them on the reef, but then we were told by a good colleague and a good friend of ours that he could find urchins under docks. So we started looking under docks near the coastline, and lo and behold, that's where we found the highest population, the highest densities of diadema urchins. So using either a Hawaiian sling or 2 Hawaiian slings or 2 metal rods, you very carefully pick up the urchins, move them onto a bucket, and then move them onto the dome site. And with a little bit of careful prodding and urging, we were able to put in 5 urchins into each of the domes. And then COVID happened. We have not been able to go out and do our post-diadema benthic transects. We're waiting for the lockdown to finish. And we will probably, what we are planning to do is to redo the pre-diadema agra measurements, install diademas if they're gone, and then wait 1, 2, 3 weeks, and then come back and do the post-diadema agra transects. And again, what the idea is to follow and do the same transects on the same sites. We actually installed markers at the end of each transect so we can find where our transect ended when it was first done. So these are semi-permanent transects that we can come back to. And that's it from me. If you want to learn more about the Healthy Reefs Initiative, that's our contact information. And it's my pleasure to pass it on to Joshua Patterson and Aaron Pilnick.
All right, thank you very much, Ian. I really appreciate the introduction. We're going to switch gears here a little bit and finish things off talking about developing intensive aquaculture to hopefully get to the point where we can grow these things at a scale that would be relevant for reef restocking efforts. So I'm Josh Patterson, that's me there on the left, with the program in Fisheries and Aquatic Sciences at the University of Florida. Aaron Pilnick is a PhD student in the School of Natural Resources and Environment. These are actually Aaron's slides that I'm presenting today. He had another virtual symposium yesterday that he had to prepare for, so we decided to kind of divide and conquer. Got to start off by acknowledging foundational information that has really helped us get to where we are as quickly as we have. So Martin Skip-Bow, photograph there on the left, has been basically a free consultant for us throughout this entire process. Also, Dave Vaughn at Moat Marine Lab was working with Skip on some larger scale culture techniques. Tom Capo's lab at the University of Miami provided some good information through data that's out there. And then John Than with the Florida Aquarium had a successful culture run around 2015 before we really got started in the project. And so these folks and others have all provided useful. Now, with all of these efforts, why are we not fully there yet, right? So culturing Diadema is extremely difficult for a number of reasons. There are commercial urchin facilities that produce animals for the seafood market. And for a number of reasons, the technologies for those species have not been transferable to Diadema. So they're extremely delicate larvae, highly susceptible to metal toxicity. The circled Diadema larvae on the right there shows the difference in morphology and biology of a Diadema larvae versus other species of sea urchin larvae. So whereas with a lot of sea urchin species, the larvae can be cultured in basically a static tank, they can maintain their own position in the water column. Diadema larvae are negatively buoyant, and a big part of the culture process is that we have to artificially keep them suspended in the water column. There's also been some developmental impediments. This is a photograph of rudiment formation. When the tube feet initially start extending from the body of the larval urchin, it's a sign that they're becoming settlement competent and ready to transition to the benthic phase. And so there have been some sort of undescribed impediments in terms of rudiment formation in the past. It's extremely labor intensive. So not only are you culturing the urchin larvae themselves, what they're eating is live microalgae. So in a commercial scale facility, you're generally probably gonna have a full-time person that does nothing but culture the microalgae that you're feeding to the larvae. And so all of these reasons have led to this sort of lack of replicated success, trying to scale these culture methods up. To where we've got, you know, thousands, tens of thousands of juvenile urchins, where we could start to begin looking at restocking efforts directly in the reefs. So to address this issue, the Florida Aquarium, where we are housed at the Center for Conservation, and the University of Florida School of Natural Resources and Environment partnered in early 2018 to begin looking at this. And so what that partnership really meant was that we were able to bring Aaron on as a graduate student and outfit this lab for to design and construct a replicated recirculating aquaculture system, which is something fairly novel for culturing this particular species. So this is the day that the custom fabricated chrysals arrived in the lab, and you notice the big smile on Aaron's face. This is a few months later. The smile is slightly smaller. Aaron has now constructed the system with some help from other grad students in the lab and Florida Aquarium staff. I'm not going to go into all the details of this system. We have a descriptive manuscript in preparation. None of this is proprietary or anything. All of this information is available to anybody who would like it. And what this allows us to do is allows really Aaron pretty much by himself to culture the microalgae as well as run replicated trials looking at different aspects of the culture process and trying to optimize those. The other thing that the descriptive manuscript has in it is our broodstock maintenance and spawning procedures. The broodstock were collected from the Middle Keys by the FWRI Marathon Lab for us. And we're spawning them using a technique that Skip developed where it's just a simple warm water bath. It doesn't always work. So about 2/3 of our spawn attempts have been successful, and that's defined as producing over 500,000 viable embryos. A couple of things from this table to point out is that we get a low overall proportion of the 13 roughly adults that we attempt to spawn every time. And so moving forward, if we, when we figure out how to culture these things at large scale, broodstock management and rotating animals in and out to maintain adequate genetic diversity is going to be an important consideration. One thing that we don't have a problem with is fecundity and producing a bunch of viable embryos. So we're getting millions of eggs per good spawnization rates, which makes it, that aspect of it at least relatively simple. In terms of how we conduct these experiments, we measure growth and survival is fairly straightforward. We use volumetric subsamples to estimate survival in our replicate culture vessels. And in terms of growth, the factor that we found that's most indicative of developmental stage is that body area. And our appendage length is relatively plastic. And so we pay the most attention to body area. And so we're just taking subsamples, measuring them, taking the mean of that as the value for that replicate tank. And we've got treatments applied to multiple replicate tanks per run. Done several larviculture experiments looking at microalgae species. We found that Rhodomonas and a diatom, Cattoceras, is sort of the ideal diet in terms of growth and survival. Microalgae density, we haven't really been able to fully hit the ceiling on that yet, I think, just because of limitations in terms of infrastructure and algae capacity. So we haven't been able to, it seems like the more we feed them, the more they grow, but that's one that we haven't been able to really dial in. And then larval density, we actually find that about 1 larvae per mil of culture volume is ideal. And that was slightly less density than we were starting out with. So that was interesting. One that I'm going to go into a little bit more is this antibiotic treatment. So we have noticed that about 30 to 35 days post-fertilization, these things usually you expect rudiment formation by around 40 days. We start to see this essentially disease set in. So we called all the aquatic vets that we knew. So Dr. Ari Festugian at the Florida Aquarium, Roy Yanong, Ruth Francis Floyd, and Sal Frasca at UF. And the photograph on the right, that tissue erosion that you see is generally an early sign of bacterial infection in aquatic animals. So that gave us sort of the impetus to maybe try an antibiotic on these guys. And so we did that in a totally one-off non-replicated trial, and were able to successfully settle some urchins from that run. So that was very encouraging and led us to further believe that what we were dealing with might have been bacterial. So we did in fact design a replicated study to look at oxytetracycline dosing. The 0 on the x-axis here is actually probably about day 30 of the culture run when we start to see the disease set in. We're getting some really promising results in terms of the effectiveness of oxytetracycline. Of course, ultimately the goal here is to do some bacteriology, histology, electron microscopy, and try to get at the root of what the cause of this is, right? So that we can change the parameters of the culture system and not have to rely on an antibiotic to grow these things. And then there's a theme that you've probably noticed running throughout all of these is that we're right in the middle of this really promising trial and the COVID strikes, so everything had to be shut down. So, however, there is some good news. We did, prior to the onset of any investigations of antibiotics, we had a successful trial where we produced 100 juvenile urchins. Those urchins actually, Bill Sharp from the FWRI Marathon Group came up, drove up the 7 hours from Marathon and picked them up. And I'll show some data on the next slide. That's some more promising data. The second batch that we produced using the antibiotics was actually just recently shipped just last week was shipped down to the Marathon Lab, and that was successful. So all the urchins were overnighted. They all arrived healthy and in good condition. So that's promising, and it saves time and resources for people. So the benthic ecology group at FWC Marathon took our hatchery urchins and ran some behavioral mesocosm experiments on them, and actually found some really promising results versus a 2018 paper using some hatchery urchins from a different source, and that indicated that those urchins sort of lost that nocturnal behavior. They were not going into shelters during the daytime. And when we produce these urchins, they go back to the greenhouse with the broodstock, and it's a natural photo period. And we provide abundant structure. And so it seems like those two things possibly have led them to retaining that natural nocturnal sheltering behavior. So that's pretty promising. Next steps are obviously to work further to address this disease issue. And then there's some other bottlenecks in terms of larval settlement and post-settlement survival that we need to address. So we had about 10,000 competent larvae on the run that produced 100 juvenile urchins. We probably had about 1,000 really early post-settlement urchins. So if we can move a decimal place or turn that 1 into a 5, those are the ways that we're really going to be looking to scale this up. So those are the next sort of steps, is to address the settlement and early post-settlement survival bottlenecks. And then down the road would be fantastic to work with some collaborators and start to look at how do we safely and effectively put these animals back out to the reef to do what it is that we're hoping they'll do for us. Tons of acknowledgements as well, multi-partner project, and then there is our contact information. And so at this point, I think I'll turn it over if there might be time for questions.
Thank you, everyone. Okay, can we get all the presenters to come back on with their videos so we're all ready, like the Brady Bunch slide that we are? So Patricia's going to put up, oh yes, we were going to put up that summary slide. Everybody sent us their main key points. So Patricia can do this, and participants, you can keep the presenters in the little panel over on the side, the thumbnails. So whoever is speaking will automatically come up and you'll be able to see their face as they talk. You like that? So I'll go ahead and start the first couple questions, although I'm seeing our faces, which is in the way of the questions. Okay, so the first one is for Dr. Lessios. How do you explain the movement of the pathogen against the current, which led to that distribution in the OECS?
You know, we look at the pictures like the ones I showed with little arrows and think that currents are a river within the sea that only go one way. This is not what happens, of course, in the sea. There are storms, there are winds. So the water moves back and forth. And what happens with, if you have a pathogen, is it only needs to move upstream for a little while for things that are reefs that are close together to actually infect the reef upstream, and then things keep going. Now, as far as the outer Antilles are concerned, I'm showing all the currents going from north to south, but in fact, now there's evidence that in fact, there is flow in the other direction as well. And of course, you know, there's, those are surface currents where one knows what's happening below them. So I explain this as the result of proximity of islands all around the Antilles chain.
Great, thank you. And just real quick, what was the last year of data collection for your recovery? You mentioned it's not exactly current, but what was the approximate?
For my recovery, it was 2015.
2015.
There have been some papers with publication dates more recent than that, but I cannot remember when the data were actually collected.
Great, thank you. Okay, now I'll ask the questions for Stacey. I'm kind of combining a couple that were all about predation, and how do you combat against predation in these open cages when you put the diadema in?
So these diadema, I forgot to mention, the last couple years we've restocked 500 at each of these reefs. And for the East Coast reefs, since I'm on the southwest of Puerto Rico and it takes 2.5 hours to get to the other side of the island, for the East Coast reefs, we fully enclosed 3 of the corrals and kept 3 open because they do escape, and they'll escape in the first 2 weeks. Most of them, not all, some stay within the corral. We didn't see really any predation. There were a couple times where we did see piles of spines. And what was pretty neat, after the 2 months where we thought that maybe they were eaten or we didn't know really what happened, once we returned to the reef, we could kind of see how they spread out. And they were hiding in their crevice. So not necessarily the numbers that we were missing in the corrals meant that they were eaten. They just escaped and found a new home. And we saw their nice clean area around where they were basically homing and inhabiting after the 2 months. So yeah, you could try to fully enclose them. We're working on now figuring out the corral where we could keep it open and kind of install like a barbed wire so they can't escape. But they're tricky. They like to escape, and they go pretty far. So if you're doing any type of restoration, I would suggest going back a couple days after, and you could find them close by, because if you wait a week, they could be 30 meters from where you place them.
Okay. All right. Thank you, Stacey. And now we're going to let Patricia ask a couple for the next presenters.
Thank you. That was a really great overview. So thank you again to all the speakers. Alwin, I wanted to combine a couple questions we had from the audience to kind of ask you more about the settlement plates, and also about just the whole process of spawning. So how do you make the settlement plates? And what are some of the criteria or guidelines that you use on where do you place those plates? And also talking about how do you, how long does it take from them to go from spawn to fertilization to larval settlement? So kind of a two-part question of talking a little bit more about the settlement plates, and then also about how long it takes for them to settle, and how often do you go out and collect and check the plates?
So for the settlement plates, we make them from artificial turf, more or less the same method that Stacey Williams explained already. So they're 10 times 10 centimeters, and we chose locations based on trying to get a nice spread around the island. And actually now we have an idea in which regions recruitment is highest. Yeah, we can look into putting more collectors on the areas that have a lot of recruitment. So did that answer the? Oh yeah, we collect them once a month. Yeah. Did that answer the settlement plate question?
Yes. Do you have like where do you actually put the settlement, like the settlement plates? Do you have certain locations that you get a higher currents, or more protected areas in around habitats? Like if someone wants to go out and kind of duplicate your survey, where you might actually decide to place these plates that they would get a higher success rate.
Yeah, we found highest success in the most sheltered areas. So with relatively less current and less swells. So that would be the area where I would look to. And also, if there's adult populations, the first guess I would put settlement plates downstream from their locations. And that would be very interesting to see if that holds true for other islands as well, other areas. And then there was also a question about spawning and time to fertilization. And I think Joyce and Aaron are way better able to answer that question, because they actually helped us develop our protocols. So yeah, I think they are better able to do so.
I'll re-ask that question when we get to Josh and Aaron. Okay, great, thank you. Max, great, wonderful photos of the Teller reefs, and just amazing that the Diadema have come back there so well. I was wondering if you could also talk a little bit more about the different structures that you made, you know, how they provided habitat, you know, the amount of flow that might be going to the areas, and just kind of some lessons learned from building those habitats that others might be able to also imitate or copy what you're doing.
I mean, the first thing to say was the study we did in Teller was very much a pilot study. And I think the first thing to say is don't do exactly what we did, but maybe take some lessons from what we did, and say that the structure, our kind of take home was that structure seems to have a good impact. I don't think the actual design of our artificial reefs would be appropriate for a wider scale. I think if you were to look at some of what Ian is doing over in Roatan, making slightly more kind of bespoke urchin homes or urchin condos, as I know sometimes refers to them as, I think that's likely to be they're likely to be a lot more permanent on the reef and be less impacted by water movement. We did have some issues with the structures of the reefs that we put out in terms of their viability and their ability to kind of stand firm if a storm was coming through, and obviously so that's definitely something that needs to be worked on, and it's something that we're kind of thinking about as we're moving forward through this as well.
So there's a question for, let me get back to it, for everyone. It's kind of a general question about the impact of sargassum. I'm looking for it again, it was near the top. You know, that we have these chemical compounds that are deterrents to development of many different organisms, and, you know, have you guys considered the growing populations of sargassum around the Caribbean and how that might affect these restoration efforts?
Who should answer this?
That was a general question. Whoever would like to, if anyone has
Can we all
looked at.
Can we all talk at the same time? My observations suggest that attached sargassum are not a major problem. What is a problem is when you have this floating carpet that block the sun, and that, of course, is bad for both the algae and for the coral. They reduce the number of the amount of light. When things are attached, Diadema doesn't seem to be interested in them, but the worst thing that can happen is that we back and forth in the waves, and they may knock a few Diadema off.
Great, thank you. Anybody else have experience?
Yeah, I could add.
Okay.
I could add on to that. So what I've noticed really when we have these large events of sargassum, I tend to collect less amount of settlers for some reason. I'm not sure if there's more predation in the water column of the larvae. I haven't really noticed here in Puerto Rico, the sargassum tends to accumulate in bays where there are not many coral reefs. So we haven't really seen it impact coral reefs. Most areas of Puerto Rico, usually the wind kind of pushes it away, and it doesn't have a tendency to settle on the reef. So I'm not sure if right now if that would affect the recruitment of Diadema to coral reefs. But I have given this floating sargassum to Diadema in the tanks. They will eat it if it's like the last thing. They have a choice of algae, what they like. So they will eat it, but it's not their favorite.
Okay,
maybe I can add on to that a little bit. Yeah. So it's known for other sea urchins that the larvae are actually induced into metamorphosis by sargassum. So we gave it a thought that maybe because of the increased amount of sargassum that juveniles settle in the sargassum. And we did a little pilot study collecting sargassum and see if we could find any juveniles, but we were not able to. So I would be interested if anyone else had a look at that, but we were not able to find any recruits into the sargassum.
Was that sargassum in nature or was that in your tanks?
That was in nature.
Okay. Yeah, there's also a lot of predators probably in that sargassum too. So.
We had a question, Melanie, for Joshua and for Aaron. This is kind of a two-part question. One, if you could talk a little bit more about the disease that affected the diadema in your aquariums. And then kind of like the million-dollar question is, how long do you think it's going to be to crack this code? Because there's a lot of efforts to do restoration on reefs, and a lot of people are looking, you know, to be more proactive and do restoration. So that was kind of a question of how long do you think it's going to be? So two-part question there.
Sure. So I guess I'll let Aaron speak to the disease a little bit more. That's actually the virtual symposium he was at yesterday was a veterinary symposium. So he was talking to a bunch of vets about this. So I'll let him speak to the disease. In terms of how long it's going to be, I mean, it's to some extent, it's an investment thing, right? So it's pretty much just been Aaron for 2 years, you know, working 40 days in a row, you know, during the culture period. We were fortunate to get some funding last fall. Actually, the aquarium got some funding from NOAA and FWC for a 20-hour-a-week biologist that helps Aaron out. And so I feel like we're fairly close. I have down there in the next 3 years. So, you know, I feel like we're fairly close. We'll start to take a deeper dive into the disease question that Aaron can speak to.
Okay, hey everyone. So yeah, in terms of the disease, we're not, you know, there's no way for us to tell if it's related at all to what originally caused the mortality to happen. In invertebrate larva culture, there's issues with vibriosis. So I think what we're observing in our culture system is more of a problem that's inherent to the system itself and the bacterial community in the water in which we're growing the actual larvae. So Alwin and Tom actually in their work in the Netherlands have shown that you know, these larvae can be cultured in really small kind of sterile media bottles, and some prior work that Tom Capo has done has proven that as well. So I think that in those types of settings, it's relatively easy to control kind of bacterial pathogens that are potentially causing an infection. So one of our challenges in trying to develop a technology that we can really scale up for restoration and to produce tens of thousands or hundreds of thousands of diadema is to understand that this probable bacterial disease that's causing this late stage larval mortality. And so we're kind of just at the early stages of really, we need to kind of first determine what the disease actually is, and we might be able to hopefully pinpoint it to maybe like a Vibrio or some type of specific bacterial pathogen. The fact that we were able to recover the larvae with antibiotics is really promising. And we really don't want to have to rely on antibiotics to be able to culture these on scale, because that introduces a series of other questions about the viability of producing these on a scale necessary for restoration. But I think that we're, you know, within hopefully the next 6 months to a year, we'll have some more information on the disease to share.
Okay, thanks. I've got an interesting one here that's just to the general group of panelists. Has anyone successfully tagged adult urchins to assess movements?
I can answer that. I've spent years of my life trying to do it. And successfully, it depends what you mean by success. You can tag them for a few days by the method developed by Carpenter, forcing a piece of latex onto a spine. And that was good enough for what Carpenter wanted to do, which was to study whether they return to the same, under the same coral after a night's surgery. After a day or so, they dropped the spine. We put a hole in them. I mean, diadema is so fragile. Even if you pick it up with forceps and scrape the ectoderm a little bit, it will eventually die. So putting a hole in it and putting a T-tag is killing, just murder. So the answer is no. There is no way to label diadema unless perhaps you can inject a microchip inside the coelom and then go out with the detector. I have not tried that. I never had mine.
So also from our perspective, we tried adding, because we just want to keep track of the brood stock and know who's a guy and a girl and who's spawned and who hasn't. So we tried just like sliding a bead over spines, and they just dropped the spines. So even that relatively short term is not really feasible either.
Okay, they will remain a little bit elusive. I think we are 1 minute past our stop time, so I don't know if Zoom is going to cut us off, but I will ask the panelists to try to take some time and look through these questions. There's more questions specifically for you that we didn't have time to get to. And, you know, if we can have several people weigh in on the answers, I think this chat, the question and answer box will stay with this on the recording. And we will be posting on the AGRA and the Healthy Reefs websites the link to the YouTube video as soon as we get it uploaded. That will be, you know, a record of this. A couple people had to leave already on the questions I noted, and they wanted to be able to follow it. So this is being recorded. If you have colleagues that would like to look at it later, you can share it with them. So I will thank
Melanie, real quickly, the website address for the recording is at the bottom of the slide that is on the screen now. So if you would like to just copy that, and we'll also paste it into the chat.
Yes, it's just not there yet, so give us some time. Yeah, by the end of the day, we'll have it up there. Okay, thank you to all the presenters. It was very informative, very fun, and to all the participants that came and listened. Thanks. Good luck with everything.
Thank you, everybody. It gives us hope.
Thank you.